Okay, it's a pleasure to be able to talk about these strange Rydberg molecules. My purpose today is to talk about this mostly from the perspective of as a molecular physics problem, and discuss the properties of these Rydberg molecule states of very long range, and some of what I feel are the outstanding theoretical issues that we're going to try to get to the bottom of. The work I'll talk about was all NSF supported, and the collaborators included Edward Hamilton, Heather Cole, Alan Dickinson, and Hossein Sadeghipour on the early work, and on the very early work, Ningyi Du, a student of mine at LSU in the 1980s, who first got us interested in these kind of strange oscillating potential curves. So, as Tillman said in his tour de force, the type of states that we're talking about involve one Rydberg atom bound to a very distant ground state atom. And it could be homonuclear or heteronuclear. Most of the systems looked at so far have been homonuclear. So, as you know, the sort of typical topology that we're used to seeing for Born-Oppenheimer potential curves is just this simple potential curve that goes down and comes back up. If you take any pair of atoms in the periodic table, you get this basic topology. And the atoms like to sit at this very simple single minimum where you have an equilibrium. Basically, what I want to look at is what happens when you get a Rydberg electron wave function of an atom and you start seeing its interaction with a ground state atom. So this leads to the contrast that Tillman already mentioned between the standard types of bonding that you learn about in your intro chemistry courses, ionic and covalent, and what I like to call now sheepdog binding. Just still trying to see if this name will catch on in the chemistry books. So why a sheepdog? I'm sure you're all asking yourselves. So the concept here is that a Rydberg electron is going around an ion if there was no ground state atom. And now, basically, in the cases we're interested in, the electron is attracted to the ground state atom. In this case, all the alkalis have a negative scattering length for the electron atom triplet interaction at low energies. And so basically, as the Rydberg electron is going around, every time it goes to its outermost periphery, it spends most of its time, out at the outermost part of its orbit, because that's where it's moving the slowest. And every time it goes by, it adds a little bit of attraction to this ground state atom. And because the rubidium atom is so heavy, it has so much inertia, this is enough to trap it, just having that tiny little bit of attraction. So it's just like a sheepdog. What can I say? What we predicted, as Tillman said, that is almost illegible. Sorry about that. Anyway, there are potential curves that oscillate here and have an outermost minimum. And in that are bound, this is the same graph that Tillman showed that had higher quality. And then you get bound states that can actually vibrate here many, many times before the molecule decays. And the second type are these kind that have the wave function that looks like a trilobite, that have a much higher density of states and are bound by orders of magnitude more, which are the polar type of long-range Rydberg molecules. So as Tillman said, this new experiment has observed these NS states in the range of n equals 35 that have spherically symmetric wave functions, and attached to the nodal pattern of the wave function, you get the antinodes causing potential minima, because the electron spends a little extra time at those antinodes, of course, And due to this attraction effect, you get this extra binding. And this is the spectrum Tillman showed, and when you look at the spectroscopy and analyze it, as I believe Jan-Michael Rost will talk about more, you can track the binding energies and see that these do follow the pattern predicted by this simple Fermi analysis. Now, one of the things I want to stress is that I view this experiment as kind of confirming the theoretical ideas that led to, of course, the prediction of these molecules in the first place. However, it's not, in my view, as simple as that, because there are still some problems lurking, some things that we need to understand better. First of all, if you look at the real comparison, quantitative comparison of these potential curves that are predicted by this Fermi analysis, you find that they are in pretty good agreement. They have the right qualitative and semi-quantitative structures, but there are quantitative differences to really state-of-the-art calculations for the lower principal quantum numbers. And so probably to really understand the spectroscopy in full detail and the decay mechanisms of these molecules is going to require an improvement going to that next level of theory. But backing up, just to acquaint you a little bit with the lower levels of the theory, that the kind of going back to work of Aumont and Francoise Massenou years ago, one of the things that we found when Ningyi Du did her thesis work with me in the 1980s is when these are the sorts of comparisons, in this case of cesium-helium, comparing this Fermi-type approach with zero-range interactions to Pascal's, which are believed to be quantitatively accurate, potential curves for cesium-helium and sodium-helium. You see pretty good agreement, but there are differences. This, in fact, to get this level of agreement already, we had to include this p-wave interaction, in this case for a p-wave electron scattering off of a ground state helium atom. This type of term had been written by Aumont, and it also comes into the theory, for instance, of superfluid helium-3, the p-wave interaction in ultra-cold temperatures, where you get the tangent of the p-wave phase shift divided by k cubed. If you had short-range potentials, this tan delta over k cubed would go to 0 in the zero energy limit. But in fact, in our problem, because you have a polarizable atom, this is actually divergent, because tan delta goes, I think, as k squared at low energies. And so this interaction actually is divergent, and this causes some tricky subtleties and problems in trying to make a quantitative theory just out of the electron atom scattering phase shifts, which is basically what we're doing with this Fermi-type treatment. In terms of just sketching quickly how the basic Fermi theory works, remember his idea was that 2 pi times the electron perturber scattering length multiplies the Dirac delta function, and that you could, in the long wavelength limit, model the scattering by this interaction. And of course, this is the basis of deriving the Gross-Pitievsky equation in BEC, the same kind of interaction. It's nowadays more common to see it in that context than in the original context Fermi developed it for, which was this Rydberg atom perturbed by ground state atoms. And the scattering length, as you recall, is the low energy limit of minus tangent delta over k. I've indicated a t because only the triplet scattering length is sufficiently large to have any appreciable role in binding in these alkali systems. And so then if you, for instance, treat this in perturbation theory, you get that the Born-Oppenheimer potential curve does in fact oscillate like a wave function. In fact, it is basically at this level of theory proportional to the square of the wave function times the scattering length. And this, of course, is only valid if you have a non-degenerate atom state, where you can use non-degenerate perturbation theory. And there were some, I first learned about these ideas from some of these early papers of François Masnu and her group. Now, some similar ideas were pointed out by Guberman and Goddard, for instance, when they were looking at helium-2. It's hard to see, unfortunately, but there are some kind of shoulders and bumps in these potential curves, which they correlated also in a qualitative way with the orbital structure of the electronic wave functions. A kind of a similar argument at a qualitative level had been used in this context in the 70s. And if you don't like the Fermi model, and why should you? There's just, really good old-fashioned quantum chemistry calculations using the state-of-the-art quantum chemistry codes. Here are some by Jung and collaborators that show oscillatory potential curves for lithium, helium. So you really, these are a real fact of nature, I think. It's clear, but oddly, until Tillman's group observed made these recent observations for the rubidium dimer, the existence of quantized energy levels in such potentials had not really been demonstrated. This is just in case you are wondering where your favorite alkali atom sits on the scale. All of the electron alkali atoms have this large negative scattering length. Well, not so large for lithium and sodium, but still large enough to do some dirty work. And so in any case, these, and there's pretty good agreement between the new value measured by Tillman's group and the predicted result for that scattering length in rubidium. But basically, all of the homonuclear and heteronuclear alkali should show this effect. And this is a little better view of that low L example, where this would be this analog of the lowest energy dimer state that Tillman's group has seen, that is bound by S-wave pairing. This curve neglects the P-wave scattering that I mentioned earlier. And one of the things I want to do is discuss how that works and what is the importance of that P-wave term, because it's rather important and non-trivial. Let me first say a few words, though, about these polar molecules case where you take a degenerate hydrogenic manifold with several degenerate levels. Then, of course, as we know from first-year quantum mechanics, you can't just simply take the expectation value of that interaction Hamiltonian. You have to calculate the full matrix in the subspace of degenerate states and then diagonalize. In this case, you get a separable Hamiltonian, which only has one non-zero eigenvalue, approximately given by this semi-classical formula. And this is what produces this state that has the stronger binding of the electron and produces polar electronic states of the molecule. We had seen these in the time of Ning Du. This is an example. We were at that time calling it perturbed hydrogenic states because they are born out of the states that have essentially zero quantum defect. And now we call that a trilobite state. And I'm sure you're all wondering why. It's because it looks like that. Okay. So now let's talk about P-wave scattering. P-wave scattering, the whole premise of the Fermi theory is that S-wave scattering is dominant. Well, if you look at the S-wave scattering phase shift at very low energies, this is electron energy, but when you get below about 10 millieV, you see the S-wave scattering dominates, but very quickly the P-wave scattering is taking off, and in fact it goes into a low energy triplet p-odd shape resonance. So you can see that as soon as the internuclear distance is small enough that the electron kinetic energy it got from the 1 over r Coulomb potential can quickly take you to electron collision energies with the perturber that are in this range, where you have very non-perturbative scattering, and where that tangent of the p-wave phase shift would in fact be infinite. So this requires a fairly careful treatment to handle this divergence in a physical way. Otherwise you get divergences and things blowing up in the theory. So one way that we attempted to go past this problem, and is very similar to ideas implemented by Kuskevadze, Chibisov, and Fabrikant, was to do set this up with a Green's function formulation, which is very hard to read. But anyway, you all know your Green's functions. You take the Coulomb-Green's function, and of course there's this Hostler, I think, Green's function. You can write this in closed form in terms of the confluent hypergeometric function. And then you can basically set up this as an integral equation for psi as an integral over the Green's function and the wave function on the small spheres centered on the perturber and on the ion core. The ion core surface gives the information about the quantum defects for the partial waves that give non-zero quantum defects, and the sphere about the neutral ground state atom that gives you the electron scattering phase shifts. That wave function on that little sphere is given by that. So basically you can convert this, solve it. You can, if you don't like the exact Coulomb-Green's function, you can do it semi-classically. It's kind of interesting because there are exactly two trajectories that go from the source point, if you think of the perturber as a source, that go from there to an observation point in the Green's function. And so it's like a two-slit interference pattern, and or four slits, because you can go around both ways around each ellipse. And that four-slit interference pattern is what makes this trilobite, interesting trilobite interference pattern. It's really already there in the Coulomb-Green's function, in other words, even without that having a perturbing atom present. Then there are equations, and you don't really want to see that, but they are there somewhere lurking. One thing that we wanted to do, though, was to quantitatively test how good these sorts of different approximation levels were. And so one of the things Edward Hamilton did was to calculate the Rydberg states of hydrogen in the field of a rubidium perturber at 3 different levels of approximation, only 2 of which are visible on this graph. But there is a solid curve, which is the Fermi pseudopotential with the diagonalization type of renormalization we implemented. Then there are the points, which are really diagonalizing a finite range Hamiltonian that gives the right rubidium phase shifts. And then there is this Green's function method, which is the dotted curve that is invisible. And as you see, they all agree, if you'll take my word for it, about the curves you can't see. However, they do have some differences. Okay, so when you start looking at really sensitive, subtle features, you're going to have to maybe worry about how accurate things really are when you're getting to this megahertz level or sub-megahertz level spectroscopy. But one of the interesting things, it's really too bad you can't see this one. One of the really important things is that shape resonance, that triplet p-odd shape resonance of the electron off the rubidium in the triplet p partial wave leads to a potential curve that looks like this, if you can kind of use your imagination. It basically, any time a phase shift rises by 1, is there a way to improve that, you think? No. Oh, that's amazing. Nicely done, Tillman. I guess that is the difference. Okay. Now you don't even have to use your imagination. The potential curve, whenever you have a rise in pi of the phase shift, like most shape resonances have, you see a potential curve that goes down in 1 in principal quantum number. Each cycle of pi in the phase shows up as a cycle in pi of the Rydberg electron, which means one change, one extra node, one extra principal quantum number. And so this is a very universal property, which I think could be explored, and we haven't explored it much, but lots of molecules, for instance, have shape resonances. And so every time a Rydberg electron interacts with one of those molecules, like N2 or SF6, pick your favorite ground state molecule, you'll see this topology of interaction potential curves. It has to be there. Anyway, the states Tillman has looked at are basically right in here. And at that time, we weren't so interested in these low L states, how they were affected, but we are more interested in the high L states, which go into what we call the butterfly potential curve, because its electronic wave function looks like a butterfly, and we're into animals at that time in the group. But in any case, this interplay between the S-wave attraction, which works here on a scale you can't even see, and this diving down, Tillman showed this diving down. What he called this other type of binding is really just the changeover from S-wave binding into this butterfly type P-wave state. And so this is a blow-up of the potential curves because the students who have the codes that made these programs have all left my group. I can't do these calculations anymore. It's sad but true. So fortunately, Jan Michael Roos sent me their potential curves so I could explore the decay of these states. Now, this is this lowest dimer state, S-wave binding dimer state, and we were intrigued by the fact that the lifetime of the molecular states is seen to be much shorter than the atomic states, and we're trying to understand that. I wouldn't say we have understood it, but we've been looking at one mechanism in particular to explore its possible applicability, and that is an inner tunneling decay. Basically, if you tunnel inward, you have these plunging potential curves. You'll be accelerating the atoms toward each other, and then they have many, many crossings that they could come out in other neutral or perhaps even ionic channels. And so basically, have tried a calculation where we calculate the tunneling integral of these states inward, and what we find using those potentials that Jan Michael's group sent us is a lifetime of 127 microseconds. And that's less than an order of magnitude longer than the experiment, which is 15 microseconds. So, okay, well, we're not real happy with that. But one of the things we wanted to see is how sensitive is this to changing the potential. In fact, if you just add the polarization potential between the ion and the neutral, it changes this 127 to 100 microseconds. And if you change just sort of randomly the potential by 5%, it decreases the potential, the lifetime of this inward tunneling process to 36 microseconds. So because you have an exponential sensitivity of tunneling to the nature of the potential, I think this possible decay mechanism has not been ruled out, but I also can't say that we have strong supporting evidence for it, and I think this question still needs to be studied a lot further. Am I getting close to the end in time? 3 more minutes before questions. Okay. Okay. So the other piece of physics that hasn't been put into our calculations, and I don't believe it's been put yet into Jan Michael's group's calculations, is the spin-orbit interaction between the electron, the scattering electron, the Rydberg electron, and the ground state rubidium atom. So in fact, what I showed you before was just one of the triplet P curves, but in fact, there are 3 triplet P resonances with different total J that have this kind of a splitting of the order of milli eV or so. And this translates, it's been included in the work of Kuskavadze and Fabrikant, and it produces splittings so that where we were showing a single curve crashing through the 30S or so, they show all 3 of these crashing through. And I think that the inclusion of this could potentially explain some of the problems remaining in the spectroscopy and also possibly in the lifetimes. Understanding the lifetimes, this physics probably has to be put in. At least that's one of the first things I would try to put in if I had someone working on this problem besides me, who actually has time to calculate things. One thing I wanted to mention, though, is that there is some other evidence from a completely different orientation for these oscillating potential curves, namely, and just as Tillman changed from ultra-cold to hot experiments, this is a similar change in that there are old experiments by Niemax's group. They also have newer variants of the same ones at much lower principal quantum numbers, n equals 10 or 11 or so, where they were seeing features going back to the early 1980s showing bumps and oscillations in these far wing line broadening spectra that were not interpreted at that time. When we began to talk to him about that, the idea came that it might be explained by these extrema in the Born-Oppenheimer potential curves of these oscillatory character that we were calculating. So for instance, this plunging state here is basically the butterfly state in the case of rubidium, but more around the 11p state. And you see, in fact, you know from classical line broadening theory, you expect at every extremum, you expect a peak or a feature in the line broadening spectrum. And there are correlations that seem to persist over not just one, but in many different spectra they see. There's a correlation between these main extrema and the potential curves. So this is, again, some of the earliest evidence in support of these oscillatory potential curves. To conclude, I just want to say that, again, I'm encouraged that the experimental evidence that's recently come out does suggest the Fermi-type model predicts energy levels and potential curves that are pretty reasonable, at least semi-quantitatively correct. I do think, though, that there is room for further improvements in this model, and, well, I'm actually looking forward to Jan Michael's talk to hear the current state of the art in that regard, because I think they're doing a pretty good job on the spectroscopy with these sorts of models. I still think also it's interesting to imagine making these trilobite or butterfly Rydberg molecules with these astonishingly large dipole moments, which afford a lot of possibilities for quantum control, which is more the interest of this group. So thanks for listening.
Thanks, Chris, for this very nice overview. Yeah, please.
Well, Chris, there's also another area in which the Fermi pseudopotential had, astonishing success. And this was in the 70s when they were considering the collision between the neutral and a Rydberg atom. But of course, the neutral was going faster, you see. But again, the Fermi pseudopotential gave the original basic physics, and then superimposed on that, one then went further along by putting in more a scattering amplitude, which varied not just on angular of scattering, but also on the energy, which is your phase shift extra P,
Sure.
phase shifts, etc. So there's further complications, but it's a nice dualism between the bound states and then even in the collision, Fermi pseudopotential was very.
Yeah, I'd kind of like to talk to you about L-mixing cross sections of perturbers interacting with Rydberg electrons, which, in the context of our other H3 Rydberg states, we need to understand better. And I have a feeling that the theory is not really complete there yet, and I'd kind of like to get your opinion about that.
Please, yeah.
Are there any bound states? It may be a little bit more subtle, but if you have a repulsive potential, the reason I ask is something basically based on some time domain experiments done by Barry Dunning and looked at by Bergdorfer and Reinhold, and also some things that we've done with half-cycle pulses and kicking in the time domain where it's a repulsive interaction. Just wondering if there's an analogy here, even if it's not completely stable, you have some sort of long-lived states where you're actually moving backwards off of that.
Yeah, absolutely. You can get these positive oscillating potential curves, and of course they'll have a tunneling decay. We've calculated some in other contexts of those. So yeah, I wouldn't stress too much that you need a negative scattering length to see this phenomenon.
I have a question on these lifetimes. So you were involved now talking about the tunneling that might lead to. Is there other effects?
Well, there's, of course, spontaneous radiative emission, and there's black body radiation. Those are, I would have thought before seeing the results of Tillman's experiment that these two would control their lifetime primarily.
Spontaneous emission, is it differing much from the atomic one?
Let's see, I don't remember. Have you calculated that in?
Well, the wave function is not really dramatically changed, so
Yeah,
then the
yeah.
matrix elements
So I
are
would guess that it's almost
One
the
would
same
expect
then.
it's almost
Yeah.
the same.
the same.
Yeah, that's what I would have guessed from the spontaneous
Right, for the low L states.
black body.
That's also
the same,
just
yeah,
the
it's the
matrix
same,
elements
actually, all the
basically
same.
that go in here.
So because it's hard for me to imagine other channels for.
Right, well, there are negative ion potentials, which we don't think are strongly Frank-Conn, allowed the coupling to those, but there's that, and Tillman's group, they are seeing ions.
Helium
Two, yeah,
plus
yeah.
ions coming out exactly at these positions where the molecules are.
But that might be because you enter into an ionic channel then.
Yeah, so if,
Yeah,
if
so this
there
would
is some
support, this
inward
would support,
tunneling,
this
then
interpretation.
Yeah, the inward tunneling
we see
could
that
be consistent with
these
that.
signals, I mean, the ratio of atomic, or say atomic ion and molecular ion signal is more pronounced if the state is further in, right? So that sort of gives some indication that it's a process that is happening at short distances.
Okay, so is there further questions? If not, thanks again, Chris, for this very nice presentation.